Hello everyone! This week we're going to go into a little more abstract topic with respect to the previous weeks. Always about solving ODEs, but with a little bit of a look at the mathematics behind some operators that we're going to look at. And in order to build that up, I'm going to spend the first couple of videos looking at linear algebra. These are things we have seen already, but with a slightly different spin, such that they would build up properly to give us the base to look further. Let's start by looking at the correspondence between maps and matrices. So imagine that you have a function that goes from the space capital X to the space capital Y. That is something that takes a point x0 and it brings it to y on the other side. So you have a correspondence. And if you can think of having a set on one side that is also transported in a set of a different shape on the other. We have seen already that f can locally be approximated by a Taylor series. So you can say that y is roughly equal to f of x0, so x0 being the point in which you know things, plus the derivative of f computed at x0 times x minus x0. And the derivative of f computed at x0 in our usual settings is a matrix. So we have been studying matrices based on this assumption. We can also talk about determinants. A determinant of a matrix is a massive formula that is, there is a sign, then every term of the matrix multiplied by the determinant of the submatrix that comes from the full matrix minus the row and the column of the element you just took. So the determinant of A is something with a constant and the term of A times a determinant of a smaller matrix. One row less and one column less. This is a recursive formula. It's very cumbersome to compute. Another option is saying that the determinant of a matrix is the sum over all possible permutations of n elements of the product of all the elements given by I and the ith value of the permutation that you just chose. Either of these two formulas give you the impression that in bigger matrices, this is a lot of computations that need to go in there. But we're still very interested in computing determinants because knowing the determinant gives us a lot of information. In particular, they're based around this theorem. If you have a matrix, a square matrix in R, then A times x equal to 0 has a non-trivial solution if and only if the determinant of A is equal to 0. This is a key theorem that explains why determinants are so important. Because one application of it is that Ax equal B has a unique solution if and only if the determinant of A is different than 0. So if you're looking at a situation and you want to find the only thing that fits in there, well, there is just one, only if the determinant of A is different than 0. If the determinant of A is equal to 0, then there are like infinitely many solutions. And that is not usually something we like. Another corollary is that the inverse of a matrix exists if and only if the determinant of that matrix is different than 0. Further on, if the determinant is the inverse exists, then it is unique. The inverse is defined as that matrix A at the minus 1 such that A times A at the minus 1 is equal to the inverse times A, and both of these things are equal to the identity. The identity matrix being that matrix with 0 everywhere except 1 on the diagonal. This is why even if computing determinant is such a computationally expensive thing to do, it's still extremely full of information. Once you get the determinant, you know that if the determinant is different than 0, that matrix has an inverse, and any linear system you can build with that matrix has a unique solution. If that determinant is equal to 0, then you know that Ax equals 0 has non-trivial solutions, and any Ax equal b has infinitely many solutions. So it is a very key element to know when you're looking at a matrix. You also know how to build the inverse explicitly once you have the determinant of A. So the inverse of A is equal to 1 over the determinant of A times a matrix built up of the determinant of every submatrix of A with switching signs. So you start with a positive sign and then you switch positive, negative all over the matrix. And in every element of the matrix you put the determinant of the rest of A. Might be a bit confusing, but I will not expect you to know this equation by heart. But there are some properties of inverses that are quite important. So for example, if A and B are both invertible, then their product is invertible, and the inverse of the product is the product of the inverses with flipped order. If we can introduce the transpose of A, that is the matrix in which we flip all the elements with the diagonal being fixed, so we flip them around the diagonal, then the inverse of the transpose is the transpose of the inverse. And the determinant of the inverse is 1 over the determinant of A. So here it's one of the ways you see that when the determinant of A is equal to 0, you have a problem, because then the determinant of A inverse is infinity, and that it's hard to achieve with a finite number of multiplication. If A is invertible, then you know that the inverse of the inverse is A itself. So you have this double loop. You come back. And for any natural numbers n and m, then A at the power n times m, A at the power n, all of it at the power m, is equal to A at the power n times m. So you can do the multiplications in any order and it's still fine. If A is invertible again, then the product of A times B, where B is a matrix, if the product of A times B is equal to the product of A times C, then B and C are equal, and it doesn't matter if they're vectors or matrices, they're equal either way. In our review of linear algebra, we're now going to be looking at eigenvalues and eigenvectors. So an eigenvalue-eigenvector pair is called an eigenpair, and it satisfies the equation A times the eigenvector is equal to the eigenvalue times the eigenvector. That also means that lambda is an eigenvalue if and only if the determinant of A minus lambda times I, where I is, again, the identity matrix, that determinant has to be equal to 0. What is the idea behind this? Well, one possible way of visualizing this is that if you take a circle in R2 and apply the transformation defined by the matrix A to that circle is going to deformate, and it's going to deformate along two main axes. Your first eigenvector and your second eigenvector. Those are two vectors that are not going to be displaced by A, they're going to stay in the same direction, but they're going to change in length. So they're going to be stretched out or rescaled depending on the eigenvalue they're associated with. Let's review a little bit also the diagonalization. We remember that if lambda 1 is different than lambda 2, then the eigenvector associated to lambda 1 is different than the eigenvector associated to lambda 2. but it is possible that lambda 1 and lambda 2 are equal, while the two eigenvectors are different. On the other hand, it's also possible that the two eigenvalues are the same and the two eigenvectors are the same. In that case, we have a singular problem, and we're not going to cover that. We're going to cover the case in which the two eigenvalues are different and the two eigenvectors are different. If A is a square matrix, we know that A is diagonalizable if and only if it has n linearly independent eigenvectors. So some time ago we said that it was diagonalizable if it had n different eigenvalues. This is a little bit stronger. We could have equal eigenvalues, but as long as we have different and linearly independent eigenvectors, we're still good and we can still diagonalize A. Just remember, A is diagonalizable if you can write it as a product of three matrices, with the first being the inverse of the last one, and the center one being a diagonal matrix. And linearly independent means that you can write that if the sum of a constant times the vector 1 plus a2, v2, and so forth is equal to 0, this happens if and only if all coefficients are equal to 0. And this happens only if and only if the matrix with all the eigenvectors written down as columns is invertible. And if you know how we diagonalize matrices, well, you know that P is actually structured exactly like this, with v1, v2, and v3, and up to vn as vertical eigenvectors. So if we have n linearly independent eigenvectors, then we have different or the same eigenvalues, we don't care, lambda 1 to lambda n, then A can be diagonalized, with P being indeed this matrix of vertical vectors v1 to vn, and D being the diagonal matrix with lambda on the diagonals and 0 everywhere else. This is equivalent to say that we have applied a change of basis from x, y, or whatever the coordinate system you started with, to a coordinate system in which v1, v2 down to vn are the coordinates that you have chosen. This is a new basis that you're used to describe your space, and in that new base, lambda 1 to lambda n are the coefficients of your new matrix transformation. As a corollary of this, because of what we said before, if A has n distinct eigenvalues, then A is diagonalizable, because having distinct eigenvalues is a guarantee to have distinct eigenvectors. Not only distinct, but linearly independent.